Udah. Yang ini kan? Udah. Hello there. Halo teman-teman. Ini siapa aja? Exact yang baru ada 2 doang. Oh ini kamu Mas Nur. Ini kamu ya?
Aku nggak ada fotonya Mas.
Oh kamu nggak ada fotonya? Udah gabung Zoom belum?
Udah. Masih.
Iya. Sip. Halo guys. Kamu muted juga. Okay, hello there. Hi all. Hi Titanio. Titanio is like seems to be joining in. There's X Alfia, then there's Al, correct? Halo Mas Budiman, apa kabar?
Halo.
Halo.
Baik.
Oke, jadi ini Cypherpunks Developer Conference yang OX02. Terima kasih teman-teman udah pada gabung. Ini semuanya pada Indo. Is there anyone here that doesn't understand like Indonesian? I don't think so. Okay, so yeah, I guess like this meeting will also be uploaded to our normal like YouTube channel, so we could share it to the others on several like cool like projects that like several of our groups has been doing or like has done in the past. And I've reached out to a couple of friends, and recently Muhammad Augi has like agreed to be presenting today. He's like sitting right behind me, and just joined Bitwyre just literally a couple of days. First of all, welcome Augi, and yeah, welcome to the community. And for you guys who has like if it's the first time for you like to join this meeting, it's like a regular meeting that we sponsor here at Bitwyre, and we used to do this for the sake of loving scientific efforts and knowledges, and we really love to have you presenting in the future. If you have any special cool projects, the project could be many things from like physics, math, computer science, and maybe if you're in chemical engineering or you're in rocket science, that's really cool too. So don't hesitate to reach out. So I guess I'll be muted soon, and I'll give the floor to Augi. And yeah, man, go ahead.
Cek.
Yeah.
Halo. Thank you for the time. In this talk, I will talk about a little bit about quantum computation. Wait. Jadi yang share desktop yang mana sih?
Yeah, itu dia. Share.
Hello. Kelihatan kan, Mas? This talk about quantum computer. First of all, I will introduce myself. My name is Muhammad Siddiq Augi Rahmat. You can call me Augi. My background is computational physics. Is anyone know quantum computer? Yes, this is Richard Feynman, the first one who proposed the idea about quantum computer. Back then in 1980, Feynman think it's so weird when we simulate a classical system. When we simulate a quantum system with classical instrument or classical computer. Because of that, Feynman proposed that we should build a instrument that help us to simulate quantum system, because classical system and quantum system is very different. The difference is in classical system, our observable is very deterministic, and in quantum system, observable behave in probabilistic way. So the quantum computer is actually research began in 1980 and until now. This is Google Sycamore. The first Google claim with this processor, Google has reached quantum supremacy. This processor is built by John Martinez and his team. Actually, I forget how much qubit in this processor, but this processor is for now is very high for the nearly quantum computer. So what is quantum computer? Quantum computer is basically built by two fundamental ideas. The first is quantum complexity. Quantum complexity is our basis thinking that quantum computing is powerful than classical computer. The second is quantum error correction. Quantum error correction becomes important when we scale up our quantum computer. Yeah. What is quantum entanglement? Quantum entanglement is like I give you some example. When we read a book, classical book, when we read page by one page, we gain some information about the book. But this way cannot do in quantum books, because when we read page by page in quantum book, we have nothing, uh, we have nothing we not gain information at all. In quantum book, when we if we now, kalau mau mengetahui informasi, we must read the book simultaneously all the pages. So entanglement is basically doing a measurement, doing observation simultaneously in quantum system, not page by page, but simultaneously all the page in the quantum book. What's make quantum computer different? Before that, we recalling our knowledge about classical computer. We know that classical computer works in bits. Classical computer can be in state 0 or state 1, true or false. And the operation in classical computer is doing with the classical gates, not, and, none, or, nor, XOR, XNOR, and such like that. So we can do operation in classical computer. How about quantum computer? Does quantum computer have a bit? Yes, quantum computer has a bit. It's called quantum bits. The difference is that qubit can be in state other than 0 or 1. Actually, is superposition about 0 and 1. So qubit can become in state 0 and 1 at the time, at the right moment, at the same time. And the same time. This is called superposition properties. How can we visualize that qubit? The idea to visualize quantum bit is with a Bloch sphere. This Bloch sphere is a Hilbert space sphere that every point in the sphere is representation of the quantum computer state. So imagine that our quantum computer with just 5 qubit in this picture can be have many steps than a classical computer. This is why quantum computers so powerful, because this is the difference. N bits in classical computer just 2 power n possible state one at a time, but in quantum computer 50 qubit is 10 power 15 states simultaneously available.
10 to the power 15, where does 10 to the power 15 come from?
This is actually 15 qubit can so much more state, but it is experimental evidence. Yeah, from Google Sycamore back then. This is classical gate. Now we think, how about quantum gates? How does it look like? Quantum gates in quantum computer is just a matrix, operational matrix. So the operation in quantum computer is assign the operator, unitary operator in qubit. Now the interesting is quantum gates. It's very different with classical gate because quantum gate must be unitary matrix. This is a conditional unitary matrix. This means we have consequence that our operation in quantum computer is reversible. That's the reason why quantum computer is powerful. Maybe if you don't take a class algebra linear, it must be a little bit difficult to understand. But I will give you a some visuals later. This is quantum gates. It's Pauli X gate, Pauli Z gate, Pauli Y gate, and Pauli H gate.
It's also called Hadamard gate.
Yeah. Yes, the H gate is Hadamard gate. The X gate is like a NOT gate in classical computer. It flips the bits. If the bit 0 and we assign the Pauli X gate in qubit, the qubits become 1. Pauli Y gate is a phase gate. In classical gate, we don't have gate like Y gate, Z gate, and H gate. Because classical gates don't have to be you don't have to be unitary matrix, right? But in quantum computer, the gate must be unitary matrix. The operation must be unitary. I will show about quantum gate. This is you can try in quantumibm.com, quantumcomputing.ibm.com, and choose the composer. Right here we have a 5 qubit. When we don't apply and get in this qubit, we see this probability is 1 for the 0 state. And we apply, first we apply X gate in qubit 0. Look. The first, the qubit is flipped to qubit 1. And the probability is 1. Of course, this is just a simulator, so the occurrence noise not included to when we compute this probability. And we talk about H gate. H gate is to make superposition state between qubit 1 and qubit the second qubit. Look, when we apply the H-Demer gate in, look, we have to superposition gate in qubit 0 and qubit 1. You guys can try if interest, and many more.
What happens if you have a C not with the Hadamard gate?
I will talk later.
Okay.
This is a visuals when we applied gate. Look, H-Demer gate to make superposition state. If we have in qubit analysis at 0 qubit and we apply H gate, the state is become superposition about between 0 and 1.
So like 50-50.
Yes. When we measure the state, it becomes collapse in 0 or and the X qubit are not associated with not gate in classical computer. Flip the qubit from 0 to 1. H and X. This is a very interesting gate because just quantum computer that have a very unique operation. It's called C-NOT, control not gate. How this operation work? First, quantum computer is very powerful because the properties of entanglement. This entanglement can make quantum computer have properties parallelism. So back in our simulator, when we applied H gate and we applied C-NOT gate, look, it's very different when we just a superposition with H gate. When we applied this gate, entanglement is create, is built. Entanglement, when we measure this state, maybe we measure you just want to know how the probability, what's the probability in 0 qubit. When you measure, you have the result 0.5, 0.7. And to measure the other state, the qubit one state, you don't have to measure because this entanglement properties assure you, menjamin bahwa kalau if the state that berjodoh dengan state nolnya itu pasti akan sebaliknya, atau if we example is if we measure the particle and the outcome is spin up, it must be the second particle is spin down. As simple as it.
Without even seeing it, you can like already like get that it's a spin down. It's seeing one state is a spin up.
Yes, without measure the second particle. It's very powerful, right? When we apply this very concept to build some new algorithm to solve many problems. Nah, but for now, quantum gate is still very limited. If we can find or create another quantum gate, it will enhance quantum computer and maybe create a fast quantum algorithm. Right now, the Google quantum is called near noise intermediate scale quantum computer. It's not fully quantum computer yet, so it's still long way journey to achieve that the real quantum computer. Nah, some implementation. This is one of kind quantum algorithm that I will research back in my thesis. In my thesis, I will simulate some molecule with this simple just algorithm. The algorithm is very simple. If we have a wave function and we call it trial function, we just vary this trial function with some parameter until we find the lowest energy. It's very simple, right? If we use classical computer, it intractable to solve these cases. But with just quantum computer, for the smallest molecule, which is H2 hydrogen, the algorithm is just like this.
That looks similar. So the Hadamard gates are pretty like symmetric.
Yes, it's very.
That's beautiful.
It's very simple, right? But when we use classical computer, it's not that fast quantum computer, and the accuracy with quantum computer is beyond the chemical accuracy. It's very interesting to research in this area, quantum algorithm and quantum gates, especially because when we dealing a quantum algorithm, we must have quantum gates, and for now, our gate is very limited, just H, 8, control node, rotation X, rotation Z. Thank you.
That's really cool. That's really cool. That's really cool. Thank you, Augi. I guess we did. Come on with you. Okay.
Can I ask a question?
Sure. Go ahead.
So this quantum computer has no real computer yet, right?
Right.
So it does it has some potential benchmark? I mean, like, is it a promising computer for us?
For industrial purpose, I don't know, but very for the scientific community, it's very benefit to benchmark this quantum computer. Quantum computer benchmark is Google has recently done generate random number with this quantum computer, and the result is it can shift the quantum computer that Google has can generate random number that classical computer cannot.
So this is the
So-
definition of quantum supremacy
Yeah.
that you mentioned.
Yeah, that's why Google claim that they have quantum supremacy.
What about the potential for, let's say, cryptography? Since you said Google tried random numbers, what about like brute forcing password, maybe?
Actually, that's a very interesting question. When Google not claim that quantum supremacy around 2017-18, we can access quantum computer free in IBM and Rigetti in many startup in America, US, Canada. But when Google claimed that Google has reached the quantum supremacy, IBM, Google, Rigetti not providing this free quantum computer anymore. It's because maybe they're afraid, and we can create some quantum cryptography.
I see. Okay.
So my DRSA algorithm is very emerging research area too. Mm.
Yeah, yes.
I see. So it's like parallel computing with massive boost, right?
Yes.
Like massive steroids. Okay.
Yeah.
Mm.
So you have numbers for benchmark or anything?
I think some research, right?
Yeah, I forget, but maybe I Google the paper.
Yeah, we could go to the Google paper. That's really cool.
Yeah.
Nature Google Quantum. Interesting.
Mm. Nice.
Hello Quantum World. Okay. That's not like Hello World in Brandon, right?
Here it's the demonstrating quantum.
Yeah. So the classical, you need to at least run the computer by 10,000 years.
Yes, this is
Or 100,000, all 10.
Oh, okay.
So he ran a short in
and this memory requirement.
Oh my god.
Oh my God, that's huge. Oh my.
Yes, that's why I choose John Martinez for Nobel Prize. 20. This is a sim for qubit in Google Sycamore. It's very programmable because IBM cannot. The IBM processor is still use microwave to make operation, but Google just very simple programmable superconductor qubit. So that's the reason why Google can scale up their quantum computer. It's
Yeah.
very small.
54 qubit, is that right?
Yeah, it's 52 qubit.
Wow.
And also a little bit about like the error corrections. So what's the difference between the Augi error and the normal error correction that we know? Is it the same or like especially just 2 qubits?
The error correction maybe still same.
Oh, it's
Yeah. But because this programmable, they can reduce it very.
like, so the Augi error is programmable.
Yes, the power error is. This engineer triumph, intellectual engineering triumph.
Yeah. Wow.
This is the I forgot the paper yang explicitly claim the time that need to generate this quantum number random.
Classical.
This is, but we can. Nah, this is the paper. Yeah, this transmon processor. This the error, Mas Dendi, quantum error correction ya.
Oh, okay. Simultaneous or doubles. Okay, cycle for Linda 3.8.
So it's very small. This is a control operation for generate quantum number. See, it's just a bunch of gate gates.
Yeah. Wow.
Nah, this is cross from this is cross interval number. This solve the 100-year problem that can 10,000.
Oh, wow.
It's very interesting. Man. We should join quantum race now.
Yeah, we definitely should have something. One thing that I could think of is maybe like trying some very simple quantum algorithms running on like Jetty or and
Yeah,
I bet you've done that.
yeah. Maybe if want to show, I can show it.
That's really cool. Sure.
Interesting.
This is for activate simulator with Rigetti platform. It's Rigetti computing. And the program is very simple, not like classical numerical methods. It imports packets. Bitwyre.
Quill is the name of the quantum library, right?
Yes, the quantum library from Rigetti. This is declare the gates, the quantum circuit, X, H, H, R, X. Simple, right? This is declare. This is declare the molecule package for chemical calculation to declare H2 or anything, and as natrium chloride. Basis is chemistry thing, but now this is the optimization. Right now, quantum computer is optimization is hybrid. So optimization not calculated in quantum computer, but still in classical computer. This I use. It's just a sci-fi package Neldermit algorithm. This the result. The accuracy is still 10 pangkat 10 power minus 8. Sorry for the. It's the result.
Okay, so what's on the left? What's on the X?
This is energy, and this is atomic distance.
Oh, okay. So
Yeah.
so you hit the transition zero.
When I run this simulation with numerical method for the simple case S2, the result is not stable. This same graph, but it's because when we use classical algorithm to simulate quantum system, the algorithm is not variational, Mas Dendi. So not stable to simulate even the simplest molecule. So this quantum computer for the scientific community is very helpful too.
Okay.
This is very very alien computing for me.
Yeah.
I guess like if this is the case that we could use it a lot for optimization problems, right? For example, like nonlinear optimization problems that we need like fast. If you have I believe when I see the experiment that you've done, like when you mentioned about that being unstable run on a classical computer, um, there might be or is that the case? This is a question since like I'm not an expert in this at all. So we would benefit from a lot of optimization. Like if we could speed up optimizations in fields that's not possible via classical computing, like you mentioned, like the lowest energy configuration of a molecule, then it means there's going to be a lot of breakthroughs in drug design, for example. If I could see something, an application here. So I guess like connection to your point, like Krishna, it's the quantum computers, the quantum algorithms would, other than like benefiting the scientific community by finding like the lowest configuration, we could like actually compute a lot of things that needs optimization that we can't do in the classical way. I could see drug discovery as one, and I could see like very hard nonlinear optimizations later on, like maybe like designs, uh, yeah, simulations, yeah.
I'm still having problem imagining superposition. Like one qubit can have 5 or
that's the hardest
states.
part. 6 states. That's the hardest part. Yeah, like I guess like assigning the probabilities is the hardest part because like in a digital computer, a classical computer will only be zeros and ones, right?
Yeah, seems that we need to understand quantum physics first to understand quantum entanglement.
Yeah, I'll mute mine. Okay.
No.
Yeah. Go ahead.
To understand quantum computer, it's just need linear algebra, not into quantum things.
Okay, that's not the physicists do it, yeah.
No, serious. Because when dealing with quantum computer is just operational like itu classical gate operation. But if you interest to simulate black hole or cosmos thing, you must run this quantum comprehensive.
Yeah,
I only understand classical physics, not the quantum one.
This is something that's I could see a lot of things would change.
What do you
For
think
example,
about the future of this quantum computer, Mas Augi?
Sorry.
What do you think about the future of this quantum computer?
My thing is
Will it replace the traditional computer or just
no, quantum computer not cannot replace the classical computer that we have.
oh,
Overkill when we just
yeah.
watch movie and this is very overkill.
Yeah.
so perhaps it's only used in maybe in supercomputer or data center.
Yeah, yes. To artificial intelligence or NP hard problem, I think that.
Oh, it can be used on artificial intelligence too.
Yes. Actually, it's more emerging too the field of quantum artificial intelligence because
Oh, I see.
back to optimization problem that we cannot solve yet in classical computer when we optimize mas Dendi said.
And what do you think about this quantum computing can be used to break encryption algorithms such as Bitcoin encryption algorithm?
Just like science, right? When somebody crack another problem, must be another improvement in RS algorithm.
Solution, yeah.
That's the word works. So don't be afraid.
Yeah, I'm started to think that we can have a Bitcoin miner with quantum computer. But,
It's very expensive.
It's just a joke.
it might be possible.
Bitcoin easily.
Possible, yeah.
Possible. Yeah. That's interesting. Of course, algorithm goal to find like hash collisions using the quantum way. I remember there was an algorithm regarding to that. Okay, I guess. Yeah. Any more questions, guys? Any more questions to Augie, maybe?
Maybe one question. Will you continue doing research on this, Augie?
No, for now, I doing research in numerical. But if Bitwyre interesting to doing this research, I would love to.
Okay, that's cool. Okay, right. It's good to have you here.
It's really good to have you here. You're a very smart, bright person. I could see a lot of potential for the quantum computing. I had advisors previously in the world of quantum computers and computing, and I mean back then we haven't even tried the quantum algorithms yet. And like seeing this happening with a Rigetti quantum computer, that's amazing. First of all, yeah, I think like once we hit a couple of months and like maybe our deliverables, we should definitely do some research on the fields of quantum algorithms for cryptography, for example. Maybe breaking it, or maybe some some blockchain algorithms like Lamport signatures that are quantum resistant, or maybe some other chains of blocks. I don't like calling it blockchains. Maybe some what's it called, consensus algorithm based on quantum computing. That might be interesting too. Cracking it might be really, really cool. To like doing SHA-256 like cracker. But I forget if that's possible yet, as like what you mentioned, Krista. That's from my experience, like finding a new algorithm using quantum algorithm is so hard. Correct me if I'm wrong. It's yeah. I remember from my experience doing the linear algebra for quantum computing. It's yeah, man. So I guess that was an amazing presentation. Augi, thank you so much, man. Cool.
You're welcome.
Sweet.
Yeah. Thank you, Augi.
Thank you.
Yeah, thank
Okay.
you, Mas Audi.
Okay. I guess Songkang isn't presenting with us today, right? So he's probably gonna present us next month. If not, like we probably should present on the financial information exchange. Yeah, so all of you guys who are here, we're probably going to present about a protocol that's known in the finance world called the Fix protocol. We're probably going to do it next month. So next month is when Song Kang, our lead engineer on like Fix development, or maybe Kristen and I, if like suddenly something is not there.
Yeah.
But anyways.
Or maybe Mas Dendi about AI.
Maybe I should do it this time. Actually, you're right. Yeah. I've been like asking people to do it. Now I need to do it myself. Okay, so again, guys, thank you so much for coming to the conference. It's growing from what I could see. And then I'll post this video on YouTube, on our YouTube channel too, so we can all watch it and rewatch it. Again, thank you for Augi for the really cool presentation, man. Okay, guys, talk to you soon. Okay.
Yeah.
See you.
Thank you for coming, guys.
See you.
Next month, you are free to invite your friend also.
Of course.
Yeah. Cool.